Here, I'll discuss the mathematical model underlying frames, and which is a superposition of the truss mathematical model and the beam mathematical model. So you combine them in an uncoupled fashion. I'll talk more about that. But one thing to keep in mind is that whether you're talking about trusses, beams, or frames, all these are based on the assumption that every cross section moves together. In trusses, because you have only axial elongation or contraction, the cross section moves in the axial direction along the midline. In beams, where you have only transverse loads, the cross section can move in the transverse direction, up or down, and it can rotate. So you're making assumptions of what the cross section can do. And in the frames, the cross section can have axial as well as transverse displacement, and then it can also rotate. Let's take a look at how this works out. So I'll consider a simple bar again to keep the discussion tractable. I'll just retreat to considering a single bar, and let's say I have simply support. It's simply supported over here, and it's got roller supports over here. And I apply an axial load. So let's say I apply a load like that. And then if I look at a cross section like that, it's going to move as a whole. That's an assumption. And it's going to move to the right. So let's say that's where the cross section gets displaced. And that distance, I'll call that u sub x. So I have to put a coordinate system. This is the usual. That's x, that's y. And once I know how much the cross section moves, as we saw in the truss case, we can figure out what the stress is, and it's going to be uniform over the cross section. Okay, and let me call that sigma x axial. And we saw that once we know the stress, we can calculate the potential energy, and let me call that pi axial. Okay, and then the problem reduces to find ux. Now that's going to be a function of x. In this case, it's going to be linear function, right? The cross section is going to move the most here. It's not going to move at all over here. So it's going to be linear function. So we have to find a linear function u sub x such that the potential energy is minimized. So to minimize pi axial. That's essentially what the truss mathematical model is. Let's now consider a second case where you take the same bar and now you apply a transverse load. So you apply a load like that. And then you look at the same cross section and you say, hey, so again, you assume that the cross section will move as a whole. It'll get displaced downwards. So it's going to move something like that. But it's also, because it's going to bend, it's also going to rotate. So the final configuration is going to be something like that. And the amount the cross section moves in the transverse direction, I believe we denoted it as u sub y in the cantilever beam example, and then the rotation is theta z. And because the extremes, due to the rotation, it's the extremes that move the most, and they have the most strain and the stress. So if I look at the same cross section and draw the stress, okay, at the pivot point over here, the stress is going to be 0, and it's going to be maximum tensile at the extreme because that's rotating the most, and then it's going to be maximum compressive at the bottom fiber. So you'll get something like that. Okay, and I'll call that sigma x bending. That's what it's usually called. Okay? And in this case, the problem then is find uyx, so how much each cross-section moves in the transverse direction and how much it rotates such that the potential energy is minimized. So this is going to be pi bending. Right, similar to being able to find the potential energy once you know the stress. Similarly, once you know the bending stress here, you can find the potential energy due to bending, and then you need to minimize that you need to find that to minimize that. Okay, now in the frame mathematical model, you combine both effects. So you have axial plus transverse loads. So you have an axial load and you have the transverse load, and the cross section then is going to move to the right, same thing, but it's also going to move down and it's going to rotate. And if these displacements and rotations are small, you can just add these two effects, and that's what the frame mathematical model does. So if I look at the stress distribution, pardon me, okay, my tablet is acting up. I just add these two. So the constant plus the linearly varying, and I'll see something like this. So my 0 will move down, let's say, and so in this part of the cross section it's tensile, and this part it's compressive. And ANSYS calls this sigma x combined, and the potential energy is going to be due to the potential energy due to the axial load and the potential energy due to bending. Essentially this value plus this value. And then you find how much the cross section moves in x, in y, i.e. in the transverse direction, and how much it rotates such that the pi is minimized. My tablet is not having a good day. Okay, so that should give you a sense of how you combine the truss mathematical model and the beam mathematical model to get the frame mathematical model. One thing to keep in mind is when we solved the truss problem in ANSYS, it was using both the axial effect and the bending effect, and we ignored the bending effect. And similarly, when we solved the beam problem, there was ANSYS was also putting in the axial extension contraction, which was 0, because ANSYS always assumes that by default assumes that you have both these effects. So that's a default. Next, let's take a look at how you solve this minimization problem in the finite element method.